The quantum mechanical model explains a lot of the things that we observe about elements. The chemical properties of the elements are largely determined by the number of valence electrons they contain. The reason that the element properties vary in a periodic fashion is because the number of valence electrons is periodic. And this also explains the reactivity of hydrogen. Remember at the very beginning of the chapter, which was a long time ago now, we talked about how the Hindenburg was a dirigible full of hydrogen and it blew up. And now they use helium because helium is not very reactive. Helium is inert because its valence shell of electrons is full. Hydrogen is very reactive because it's not full. Its valence shell is not full. When we look at the noble gases, what we observe is that helium is a small guy, a little element, but its highest occupied shell is full. The 1s shell is full with 2 electrons. The rest of the noble gases have 8 electrons in their valence shell. And these are particularly stable. They're very unreactive because of this. They are unreactive because this is a particularly low in energy condition for the elements to be in. Group 1a, these elements differ by 1 electron from the noble gases. Sodium has 1 more electron than neon. Potassium has 1 more than argon. Argon is very stable and inert. Potassium is unstable and reactive. Because if potassium loses that 1 valence electron, that's the outer shell of the onion. It's just got a little piece there, and you pick that off, and then it's got this nice, smooth, full shell. When potassium, actually any of these, when they lose 1 electron, then they have the same electron configuration as a noble gas, and that's particularly stable. So they will very easily react in a way to form a +1 ion, because that makes them more stable. The alkaline earth metals, these are the ones in group 2a, and we learned that these form 2+ ions, right? We just kind of learned that back in chapter 5 as a way to help us with nomenclature. But all of these electron configurations show that there's 2 valence electrons. If these guys lose those 2 electrons, then they have the same electron arrangement as the next smallest noble gas, which is very stable, and so they tend to do that. These guys are not as reactive as the alkali metals, but they're still fairly reactive. If we look at the halogens, group 7a, we see that all of these elements are 1 electron short of a noble gas configuration. If fluorine could gain 1 electron, it would look like neon in terms of its electrons. And so it will react in a way to do that, and all of these guys form -1 ions because in doing so they gain a noble gas electron configuration. And so that's why we see this pattern with the the ion charges. These guys gain 1 electron because they need 1 electron to move over here. Nitrogen needs 3 because it needs 1, 2, 3. By gaining 3 electrons, it becomes like a noble gas. Calcium loses 2. It goes 1, and then this guy jumps way over here, and he becomes like that one. Aluminum has 3 valence electrons, so does gallium and indium. They're going to lose those 3 valence electrons. Aluminum loses 1, it becomes like magnesium in terms of electrons. It loses 1 more, becomes like sodium. It loses 1 more, it becomes like neon. So in my chemistry land, the noble gases are the cool kids, and everybody else is trying to dress like them and fit in with them. You can't change who you are. The elements cannot change the number of protons. The number of electrons can change. It's like the clothing of the atom. It's on the outside. You can change your clothes. You can't change who you are.